So here's a little video for you guys to walk you through the mechanisms that are part of the homework for our lipids chapter. So these homework question numbers are questions number 3, 10, 14, and 16. So 3, 10, 14, and 16. So I'll deal with them each independently here. So the first is asking us to draw a mechanism to show the acid-catalyzed hydrolysis of an ester. So first here, I just kind of want to highlight, let's draw an ester here. Because anytime we're doing anything in an acid-catalyzed sense, we have to ask the question, well, where do we protonate? Clearly, we're going to protonate a heteroatom, but which heteroatom is better to protonate? So to see which heteroatom is best to protonate, draw resonance structures. So again, I can draw a resonance structure here that puts the negative charge on this oxygen atom. So by putting the negative charge on that oxygen atom, that tells me that this is where it is best to protonate. Because if I were to draw a resonance hybrid, I would see that this oxygen atom is going to have a partial negative charge. This oxygen atom is going to have a partial positive charge. So again, if we're protonating, we're going to be putting it on the most nucleophilic atom. So let's go ahead, and it's okay if you don't necessarily draw the protonation step to show this guy being protonated. But this is going to be our important electrophile here. And doing this in an acid-catalyzed sense just makes this species more electrophilic because our nucleophile here is water. And water is not a great nucleophile. So we can help this situation by making our electrophile more electrophilic. Just a little side note, you can actually help do ester hydrolysis by actually making the base more nucleophilic. So we can actually have chemistry with hydroxide. This is called base promoted rather than acid catalyzed because the base actually is used in this process. So by creating a basic situation and having a higher concentration of hydroxide, we can actually facilitate this chemistry. Okay, so one of the things that I'm going to highlight to make this mechanism a little bit shorter than maybe we had when we did this in Biochem 1 is I'm going to combine some protonation and deprotonation steps with some chemistry. And that just allows us to make things a little bit more compact when we consider a mechanism. So again, I'm going to have my base come in here. I'm going to have a base acting, again, as a general base. Is going to deprotonate water, making it more nucleophilic. That water is going to nucleophilically attack our electrophilic carbonyl carbon of our protonated ester here. And those electrons are going to come back up here to allow us to generate our tetrahedral intermediate. And you'll notice that the intermediate we generate here is neutral because we already did that deprotonation step. Okay? So now what we can have is, again, I'm going to combine things together here just to make my mechanism a little bit shorter. I'm going to have a base here now acting, and I'm going to have an acid down here. Let me just walk through what we need to happen first. We want to have this tetrahedral intermediate decompose, and now what's going to come off is this guy as an alcohol. So we're going to need to protonate him. So I've got my acids kind of positioned nearby to do that. And yes, I could have this guy kind of decompose and generate our pi bond here while still keeping that hydrogen there, and I'd have a protonated intermediate or a protonated product there. But I'm going to kind of have this happen all at once. Okay? So again, it's okay to combine protonation and deprotonation steps with chemistry. What we sometimes don't want to be doing is kind of combining too many chemistries together that might not happen in kind of a concerted fashion. All right, so we're going to deprotonate this guy. That's going to allow us to reform our carbonyl double bond there. Can't have 5 bonds to carbon, so something needs to leave. And this guy leaves best when it's protonated. Okay, so lots of arrows there, but we end up generating our carboxylic acid, and our alcohol. And it's okay again that this carboxylic acid stays protonated, because remember, we're in an acidic environment, so it's going to be okay that we keep that species protonated. All right, so that's homework problem 3, the mechanism for that one. All right, so let's go ahead and do number 10. So 10 is draw the mechanism for a reverse Claisen condensation. So we're going to hydrolytically cleave a carbon-carbon bond, and we're going to use a beta-keto thioester, and we're going to then generate a thioester and a carboxylic acid. All right, so this is going to again be hydrolytic carbon-carbon bond cleavage. So let's go ahead. This is homework question number 10. Let's draw our thioester here. So our beta-keto thioester. So again, part of some of these mechanisms is just kind of making sure that we're comfortable with some of the functional group nomenclature so that we could draw the correct species. So again, this is at the beta-keto, or at the beta position, there's a keto group. So here's our thioester. At the beta position, we've got a ketone. So that's a beta-keto thioester. And so what we're going to do here is we are going to first nucleophilically attack our beta-keto group using water as a nucleophile. Like I did in my last mechanism, I'm actually going to make this a better nucleophile by protonating it. So again, I'm going to make a better nucleophile by deprotonating it. So I've got a base there to deprotonate this water. Better nucleophile, nucleophilically attack, and generating a tetrahedral intermediate. In this case, because I know this is going to decompose, I'm not going to bother trying to sort of protonate it. Okay, so we've got our tetrahedral intermediate that we have here. And I'm actually just going to remind us, rather than kind of combining protonation steps here, I am going to kind of show this in one step because I want to remind us why it's okay here to break this carbon-carbon bond. So if I break this carbon-carbon bond here, I'm going to be generating our carboxylic acid here. That's our first product. And then I'm going to draw this intermediate as the enolate that we have here. But remember, when we have an enolate, the reason that it's okay to sort of break this bond and why this bond is considered labile, just like when we had a beta-keto acid, a beta-keto carboxylic acid, we could readily decarboxylate that. Breaking that carbon-carbon bond to generate a carbon nucleophile is okay because we can resonance stabilize these electrons through the adjacent carbonyl. So I'm just going to kind of show that up top here so that we can remind ourselves and remember why this is so easy to break a carbon-carbon bond and generate a carbon nucleophile here, is because we can resonance stabilize these electrons through the adjacent carbonyl carbon. Okay, so that's the resonance structure that reminds us why that is so stable. But what we're actually going to have here, and I'm just going to cheat a little bit here, and I'm going to move this over here so I have a little bit more room, is we're actually going to do chemistry from this enolate. And so all we need to do is protonate this enolate, so we need to have an acid that's down here that we can take a proton from. So whether we actually took these electrons and protonated, or as you're going to see here, I'm going to move these electrons down. And once I move those electrons down, I can take those pi electrons and use those to protonate. Both end up with the same product here. And that product, again, here is going to be our thioester. So again, this problem asked us to start with a beta-keto thioester and then generate a thioester and a carboxylic acid. So here's our thioester and here's our carboxylic acid. Okay. So a really important thing that we're going to see in a lot of chemistries here is when we have beta keto groups, or we have a carbonyl at a beta position to another carbonyl containing functional group, we're going to see lots of chemistry that can happen between that alpha and beta carbon. Normally, we don't think about carbon-carbon bonds being something that are easily formed or broken biochemically. But because we have these unique functional groups here that allow for species that are carbon nucleophiles to be resonance stabilized, we can do a lot here with, in this case, breaking a carbon-carbon bond, or as we'll see in subsequent mechanisms, forming carbon-carbon bonds. All right, so let's move on now to reaction mechanism, I think it's 14. Okay, so reaction mechanism 14. 14 and 16 are kind of related, as we are going to see sort of two mechanisms and ways for generating carbon nucleophiles to do chemistry. Okay, so let's start first with 14 here. It says, draw a mechanism for the Claisen and condensation between a thioester and an alpha keto acid. So it asks us to do it with acetyl-CoA and oxaloacetate. So we're really looking at the chemistry that happens with citrate synthase. So let's first draw oxaloacetate. All right, so this is oxaloacetate. And we're going to do chemistry with acetyl-CoA. Okay, so it's hydrogen I want to draw here. Hydrogen. I'm just showing the hydrogen that's on that methyl group there. So one of the things too that I'm going to do is I'm just going to number my carbons here, so it's easy to kind of put these pieces together. Good idea to do, especially when you're doing carbon-carbon bond forming reactions, so that we kind of want to see where things end up. So again, this is the chemistry that happens with citrate synthase. So kind of highlighting here, this is citrate synthase chemistry. So how we generated a nucleophile with citrate synthase is we actually, in the enzyme active site, we're able to deprotonate this alpha carbon. So in some of our mechanisms that we learned last semester, we learned that the alpha carbon can be considered acidic because, again, putting a negative charge on that carbon atom, it can be resonance stabilized through the adjacent carbonyl. So we can, again, go ahead and let me just show that for you guys. So again, if we were to deprotonate here, generating essentially this carbanion, we can resonance stabilize these electrons through our adjacent carbonyl, highlighting that this is not an uncommon thing to do. It's not difficult to deprotonate that hydrogen from that carbon atom because the resultant conjugate base is stabilized. That's a big theme that we saw, right? If you want to ask yourself how acidic is a hydrogen, take it off. Look at the conjugate base. Ask how stable it is. If you have a way to stabilize a conjugate base, that means that that species is a bit more acidic. Okay, so let's imagine now that we are taking, and I'm going to kind of have my mechanism kind of begin with this guy. So again, this guy is going to be my nucleophile. So this part that I just kind of had in the middle here was just to remind us of sort of what happens when we generate this enolate and why it's able to be deprotonated at a carbon atom. Okay, so now I'm going to take this guy. This guy's going to be my nucleophile. Oxaloacetate is going to be my electrophile. And what we're going to see is that this specific carbonyl carbon is the one that is electrophilic. So again, just highlighting here, oxaloacetate is going to be my electrophile. I'm just going to kind of go ahead and redraw this guy that's over here just to make things simpler with my mechanism. I'm going to redraw that over here so that we can just see what's going on a little bit better. So here again is my resonance stabilized. Just to highlight one other little thing here. we've got two potential resonance forms that we have here, right? So this guy has the negative charge. I guess we should make sure we put a negative charge on there. This guy has the negative charge on the carbon that we want to be nucleophilic. This guy has the negative charge and that extra set of electrons on the atom that is more electronegative. So this guy is more stable. This is the guy that we want to do chemistry with. All right, so let's see the chemistry that happens here. All right, I'm going to move these electrons back down because I want these electrons to be acting and doing chemistry from the carbon as the nucleophile. So I'm going to take these electrons, they're going to come over here and react with this third carbon in oxaloacetate, generating a tetrahedral intermediate. Now again, I'm going to go ahead and actually make my mechanism a little bit simpler, and I'm going to not have to draw a second step here to show protonation. So rather than moving these electrons right here up onto that oxygen and then have to do a subsequent protonation step, I'm actually going to have them grab their proton right now. Okay, so what we're going to see here is my final product, and I'm going to actually set this up like we see citrate. Remember, the product of oxaloacetate and acetyl-CoA is citrate from the citrate synthase reaction. Okay, so here is the structure of citrate, not drawn as a skeletal structure, but drawn like we're used to seeing it in our citric acid cycle sort of set of intermediates. And again, I'm going to go through here in a second and just highlight numerically where all these carbon atoms come from. So we've got carbon 1, 2, 3, and 4 that come from oxaloacetate. And then we've got carbons 5 and 6 that come from acetyl-CoA. So remember when we talked about this chemistry happening? Carbons 1, 2, and 3 sort of stay in a straight line, and we imagined making a bend. So that's oxaloacetate that we have there. So this is the new bond that was formed there. And again, this is the carbon that was nucleophilic. One of the things that we actually didn't show here is this is after hydrolysis. So in reality, we would have the first product that we make would be this carbon atom, carbon 6, actually still having the CoA as part of it. But I'm just going to kind of highlight here that we can have water come in, and then we're going to have CoA come off. So we're actually going to hydrolyze that ester. So again, just taking a little bit of a shortcut there. Apologies that I didn't kind of comment on that. That's why that becomes a free carboxylic acid, because we're going to have water come in, nucleophilically attack, and then we're going to expel protonated CoA there as CoA, should say CoASH. And we're going to generate then citrate as our product. Okay, so why I had you do this mechanism and why it's important to think about is this is one way to make a carbon nucleophile. One way to make the a carbon nucleophile is to deprotonate an alpha carbon's hydrogen. And again, deprotonating an alpha carbon's hydrogen is okay because that enolate can be resonance stabilized. Okay, that chemistry tends to need the assistance of an enzyme active site because you have to have an amino acid residue that's going to serve as that general base and facilitate that deprotonation in sort of a protected environment there. But that is one way to make a carbon nucleophile. Okay, so mechanism 16 kind of connects with this in the sense that we are making another carbon nucleophile, but we're doing it in a different fashion. So remember, we had to reword the writing in this question. We basically just said write a reaction mechanism for the decarboxylation of a beta-keto carbonyl compound. So it says use malonyl-CoA, and then we added show the chemistry with acetyl-CoA. So we're going to draw malonyl-CoA here. So here is malonyl-CoA. So here's malonyl-CoA, and then we're going to react it with, again, acetyl-CoA. And just to highlight and just review a little bit, remember we're going to have, let me put this in blue here, talking about where these species are on our fatty acid synthase machine. This guy is attached to Ks, and this time acetyl-CoA is going to be our electrophile. Malonyl-CoA, which is attached to the acyl carrier protein, is going to be our nucleophile. Okay, so pretty simple mechanism to kind of show what happens here. And in this quote-unquote mechanism, I'm actually going to take a little bit of a liberty, and I'm going to show kind of a mechanism light. Okay, so we're going to call this mechanism light, where some of these arrows, again, we're going to show things happening in more of a concerted fashion than they really do occur. All right, so when we have a beta keto acid compound, which is what we have, malonyl-CoA is a beta keto acid. So again, here's the beta keto group. We've got a carboxylic acid. We know that these readily decarboxylate, so let's go ahead and show that. So this is how we'd make our CO2. And again, we would be taking then these electrons and using them as a nucleophile. Now, if we wanted, let me just take a brief moment and just kind of highlight what this could look like. Okay, we could take and put those electrons right there, and we would be generating, there's our CO2 that we generated, and then we'd have this guy as our decarboxylated malonyl-CoA, right? We could draw a resonance structure that takes and moves these electrons. Just like we had on our last mechanism, we could generate a resonance stabilized intermediate here. And again, this guy's going to be our nucleophile. So I'm going to just kind of start from the bottom down here. We could push these electrons down, and then we're going to have nucleophilic attack here. This is where I'm going to do mechanism light. Generates a tetrahedral intermediate, decompose the tetrahedral intermediate, and then have our leaving group leave. So this part is what we'd be calling mechanism light. It's not how we truly draw a mechanism, but we've done so many mechanisms now. I'd like to think that you guys are pretty good at kind of recognizing the intermediate steps that we'd have there. So let me go ahead, and again, I'm going to number my carbon atoms that we have here. So again, we're going to have, let's do 1, 2, 3, and then 4 and 5. And this is going to look a little bit weird here because we're going to have carbon atom 3 ends up over here with carbon dioxide. But then what we end up here is with, attached to our acyl carrier protein, not a 2-carbon piece, but we've got a 4-carbon piece that is now attached to that acyl carrier protein. And we've liberated free CoA so that it can go on and do additional chemistry. So again, if we kind of start numbering things here, these first and the second carbons were from our malonyl-CoA that was attached onto the acyl carrier protein. That was our nucleophile. And then we've got carbons 4 and 5 that came from CoA. I'm sorry, from acetyl-CoA there. So we've hooked these guys together. We made a new carbon-carbon bond. So again, why did I have you do all of these? Remember in this, we talked about one way to make a carbon nucleophile is to actually deprotonate the alpha carbon's hydrogen. Another way to make a nucleophile, another way to make a carbon nucleophile is to do our trick of, that's not of plus CO2 and then minus CO2. So remember, when we had acetyl-CoA here, we used the enzyme ACC to make malonyl-CoA by adding CO2. And then we decarboxylate malonyl-CoA to make this beautiful nucleophile that we have right here. And then we react it with another CoA to generate our coupled product, which is essentially the net of 2 acetyl-CoAs coming together. So then again, this really generates our acetyl-CoA nucleophile, which is going to react with an acetyl-CoA electrophile, and we make a carbon-carbon bond. So hopefully that made sense. Again, 4 mechanisms that we had here for this lipids metabolism homework.